Hello, everybody. I'm so happy and, to tell you the truth, somewhat overwhelmed that you all could make it to this webinar. For the next 45 minutes, we are going to take a well-deserved break from politics and stuff and instead talk about loudspeaker modeling using Comsol multiphysics. I'm Linus. I'm managing a team of global tech support engineers in Comsol Stockholm office, and I'm glad to be here with you today. We've got a lot of ground to cover, but I'll still try to find the time to answer some of the questions you might have. So I'm planning to stop and do that a couple of times over the course of the presentation, but feel free to submit your questions as soon as they pop up. A quick general introduction first. Comsol Multiphysics is an integrated modeling, simulation, app design, and app deployment environment. You set up multiphysics models in which you couple equations from one or many different fields of physics. You can also define and use your own equations. Once you're happy with your model, you can quickly and easily turn it into an app. This lets your colleagues and customers, even those that are not familiar with modeling, use your work. Comsol has a wide range of functionality for acoustics modeling. I'll cover the main parts. So pressure acoustics is what you normally use for modeling acoustics in fluids, so typically air or water. Mufflers are a common application. With acoustic structure interaction, you get to model structural vibrations and the way they interact with pressure acoustics. This is key, of course, in loudspeaker modeling. You will have vibrating parts such as the speaker membrane. Those are what create the sound and thereby drive the pressure acoustics equation. Thermoviscous acoustics is required in small and narrow geometries. Cell phone speakers and microphones, for example, or as in this image, an artificial ear canal. Aeroacoustics is acoustics with a background flow. It can be jet engines or just as well mufflers with a gas through flow. You can bring in your background flow from measured data, or you can model it with Comsol CFD interfaces. In very large geometries or at high frequencies, a more approximate geometrical acoustics approach is often the way to go. This can be either acoustic diffusion or ray tracing. If you want to model electroacoustics, you'll typically use functionality from Comsol's AC/DC module in addition to the acoustics module. Those are the two modules that I'll use in my demo today. You can model loudspeaker drivers just as well as entire speakers, cabinets and all, or piezoelectric transducers, electrostatic microphones, flow sensors, etc. These are all multiphysics applications, and they suit our software very well. In the image, you're looking at a so-called tone pills, which is a piezoelectric transducer. You can get all sorts of relevant results, of course, from your model. Some entities that are of interest in loudspeakers include electric and mechanical impedances, as well as near and far field sound pressure levels, directivities, and so forth. In today's demo, I intend to model a loudspeaker driver, nothing less. In an experimental setup, you might mount this driver in a hole in a large reflective surface. In the model, we can make that an infinitely large plane, also known as an infinite baffle. To make the model a bit more manageable, we'll consider a rotationally symmetric driver, meaning we can model it in an axisymmetric 2D geometry. So if you look at the driver in the illustration here, this is exactly the geometry that we'll model, but we need only use its cross-section in the RZ plane. Some results that we'll get out of the model include the local sound pressure distribution in the air surrounding the driver, stresses and strains in the cone, as well as the spider and the surround. We'll get the sensitivity, which is defined as the sound pressure level on axis at a 1 meter distance given a nominal driving voltage. We'll also get the speaker impedance, and all this over a range of frequencies. Now, just a quick recap of how electrodynamical loudspeaker drivers work. We are going to apply those same principles in the model. So you have a permanent magnet assembly that creates a static magnetic field across a thin gap in which the voice coil travels. Your driving AC voltage creates a current through the voice coil, and with that you get an AC magnetic field. Now the permanent field and the AC fields interact, and you get a harmonic driving force acting on the former and the cone. This motion is what creates the sound. Of course, in reality, if you listen to music, the driving voltage will carry the signal, but here we want to see how the driver performs over a range of frequencies, so our signal is going to be just a simple sine wave for each frequency. Now, I described how the driver works in a rather linear A causes B fashion, right? But it isn't quite that simple because there are interactions going on both ways. One important aspect is that not only does the motion of the cone create a pressure wave, the pressure also acts back on the cone, which affects the vibrations. Then there's the back EMF, which is what you call the voltage induced in the voice coil by its own motion in the permanent magnetic field. And these effects are very important to include in the model. We are going to have to make sure that we do so. Just a few more things that I wanted to mention before we get going with the model. We are going to use a static solver to find the permanent magnetic field. It is a fairly strong field, and the iron in the core is just barely capable of supporting it. More precisely, the iron has a nonlinear BH curve. So it's highly permeable if you just apply a small field, but if you apply a higher field, it's going to gradually become saturated. This effect is included in the stationary study. To model the AC driving and the resulting sound and vibrations, we're going to use a frequency domain study. One type of such studies is called perturbation, and what it does is treat the considered physics as a small linear perturbation to the static solution. So by choosing that, the eddy currents forming in the core will automatically experience the iron in its partially saturated state. All right, I realize this is a lot to digest. We will get modeling in just a few seconds, but meanwhile, I have two questions that I would like to answer. What mesh sizes were evaluated, and at what size was convergence achieved? We will get to that in the model, actually. I'll set up an interesting mesh. In second, can we get the results of the electrical current as a function of time? Yes, that's an excellent question. I'm going to use frequency domain modeling, which means I'm looking at one frequency at a time using complex numbers. But you can also set up a fully transient model in which you really get results as a function of time. And that's relevant if you have nonlinear materials, for example, or if you have just a pulse that you want to send in. But in this model right now, I'm going to stick to the frequency domain. So let's open up the software. I got it right here. All right. So let's begin with a new model. We'll use the model wizard for the first few steps of this model. Space dimension, first of all, will have to be axisymmetric 2D. For physics, we are going to pick from the AC/DC branch magnetic fields, like that. I'll click Add, and this now appears under Added Physics Interfaces. We will also need acoustics, acoustic structure interaction, acoustic solid interaction. Now this gets me two interfaces, in fact, pressure acoustics and solid mechanics. I also get a multiphysics coupling, which will automatically connect those two. As we talked about, I will be running two studies in this model. First, a stationary study for the permanent magnetic fields, and then a frequency domain perturbation study for the AC fields and the acoustics. The model wizard lets you select one of these studies, so I'll pick up the stationary study for a starter, and then I'll add the frequency domain perturbation study later on. Now clicking Done brings us to the Comsol desktop and the model builder. This is the model builder. So I'm going to build up the model by adding things roughly from top to bottom in this model builder. That means we'll start with the geometry. We'll add some materials, set up the physics. As you can see, we've got magnetic fields, pressure acoustics, and solid mechanics. We'll then create a mesh. We'll run the study, and we'll finally look at the results. So geometry, I'm going to import the driver geometry. This MPH bin file happens to be Comsol's own file format, but we support most common CAD file formats in 2D as well as 3D. I'll bring that in and click on Build All Objects to see this geometry. So this isn't quite the full geometry that I would like to model. One thing I want to do is place the driver in a baffle. So I'm going to draw that as a rectangle. I'll select rectangle from here. I'll zoom in a little bit, and I'll draw it like this. Let's make it a little bit wider, 0.1 meters. Like that. We'll build all objects and zoom out. Okay, this is looking better already. The next thing, which you'll always need when modeling pressure acoustics, is an air domain. I'm going to make that a circle. So I'll right-click on geometry and select circle. I'll give that a radius of 15 centimeters, like this. Now, we'll of course want to end up with a half circle, not a full circle. We want to cover only the positive RZ plane, just like the rest of the geometry. But as you'll eventually find out, anything in the negative RZ plane will automatically be cut off the second we leave the geometry mode, so we're fine with a full circle for now. Now, the outer boundaries of the air domain should ideally be transparent to sound. We don't want them to cause any unnecessary reflections. And one way we can achieve that is by adding an outer layer to this air domain. In this layer, we are going to apply a so-called PML, the perfectly matched layer. And this is what's going to absorb the outgoing sound. A thickness of, say, 3 centimeters is fine. The PML is automatically going to be scaled mathematically internally. So the physical thickness that you give it doesn't really matter as long as you resolve it with a sufficiently fine mesh. Now we'll consider this baffle to be perfectly rigid. So we can model it as just a sound hard surface. Since there isn't going to be anything relevant happening inside the baffle, we can choose to remove it entirely from the geometry. And I'll do that by constructing the difference between the air domain and the baffle. If I hit build now, you can see that the baffle will disappear from the geometry. Now this concludes the geometry. I'll click somewhere outside of the geometry, like here, and as you can see, all that remains is the right-hand half plane. The way I've worked with the geometry right now is fairly representative of what you do in loudspeaker modeling, in fact. You'll usually have a CAD file of your speaker that you will want to bring in. It's rare, of course, that this CAD file includes an air volume, so you'll add that within Comsol, along perhaps with some other details that weren't included in the CAD file, such as the baffle in this case. Now, of course, if you don't have a CAD file, you can also choose to draw the driver entirely within Comsol. Now, I've created a space for the PML to reside in. Let's add the PML. You do that from Definitions, Perfectly Matched Layer. Just select the relevant domains, and that's it. Next up, the model will use a number of parameters. We'll define them globally. There are quite a few parameters, so I've actually prepared a file that I will import. Normally, you just type in your parameters, of course. Great, so we get things like the remnant flux density in the magnet, we get the number of turns and the driving voltage of the coil, etc. I want to add and assign some materials to the model. So I'll add material, and we'll need from built-in, we'll need air. We also want to use a soft iron material, this one. And then I prepared a user-defined material library containing 5 more materials that I want to use in the model. So I'll add them as well. We can just try to close the Add Materials dialog box right now because we don't need it anymore. Next thing we want to do, of course, is assign those materials to the appropriate places. So air, being the first material that I've added, by default applies everywhere. We are going to override this setting by applying the other materials to the domains where they belong. So soft iron, that goes to the core of the driver assembly, these 2 domains. Composite, well, we're going to have the cone made out of that. So the cone would be these 2 domains. Cloth, that goes to the spider. We'll have foam up in the surround. We got the coil down here. And finally, the former is made out of glass fiber. You may notice that some of these materials actually lack a couple of material properties. So for example, the glass fiber that I've used here doesn't have a speed of sound. And that's okay, because only the pressure acoustics equation requires the speed of sound. Solid mechanics, which is what we'll be modeling the glass fiber, takes the Young's modulus and the Poisson's ratio instead. Let me now have a quick look and see if we have any more questions that I can answer right now. I'll try to, drag out my little questions panel and see what I have received. So, the design engineer will apply a swept frequency to the speaker and measure the response a short distance away. Typically, this is done in an anechoic chamber. Can I simulate this in the Comsol model? Yes, indeed. In fact, the PMLs will sort of constitute a perfect anechoic chamber. All sound just disappears towards infinity. So that's what we're doing now already. And you measure the response a short distance away. Sure, I'm going to do that as well. Next question. The design engineer will often look for undesirable resonance patterns across the speaker cone at a single frequency of interest. Typically, the speaker is placed on an optical bench. A strobe light is used to freeze the speaker motion. A laser is also used. That's a long question here. Can I get a 3D picture of the cone displacement pattern at a single frequency? Indeed, we'll get that too in the model. Let's go back and proceed to work on the model, and we will eventually hopefully get there before the time is out. Magnetic fields is the first physics that we're going to apply here. We have this magnetic fields applied per default everywhere in the model, except in the PMLs. Now it suffices for us to model the magnetic fields in the vicinity of the core and the magnet assembly. So let's clear the selection and include only those domains. So we got the permanent magnet, the assembly, the former, the coil, the spider, and most importantly perhaps the air domain, because that's where the fields spread out. We got a couple of settings to make in this magnetic fields interface. So first, let's apply an Ampere's law node for modeling the permanent magnet. In and of itself, this node doesn't do anything because we already have another Ampere's law node up here defining, applying per default everywhere. Now, what we will do in this magnet is we want to change the constitutive relation to remanent flux density. The magnetization is going to be along the z-axis. The magnet points in the positive z direction. So I'll enter B0 for the z component. And B0 is one of the parameters that I brought in under global definitions. It evaluates the 0.4 Tesla. Now recall that we'll be running a stationary study followed by a frequency domain perturbation. And if you just type in B0 like that, it will have an effect only in the stationary study. So we get a permanent magnet pointing in the z direction, and that's it. There's no time harmonic contribution from this. And that, of course, is exactly how we want the magnet to behave, so we'll leave it like that. Next up, we need to add a separate Ampere's law node to the core. So here and over here. And this time it's because we need to point out that we have a nonlinear permeability given by an HB curve. Okay, now this HB curve comes from the soft iron material that we have applied. You can plot it if you like. You go to HB curve here, interpolation. This is the interpolation table that we're using for this HB curve. And it looks like this. So you have the H field on the y-axis versus the B field on the x-axis. To apply the coil, you just pick a coil from the magnetic fields interface. It goes over here. That's the coil domain. This coil has several turns, so I'm going to make it a homogenized multi-turn coil. How many turns? Well, n0, that's another parameter that we have defined. I believe it's 100. We have the wire diameter as a parameter as well. Let's make that d0. And we are going to drive the coil with a voltage v0, again a parameter. Now let's pause for a second here. Pay attention to this, because if we were to type in just v0 like that, it would give us a permanent contribution, like the permanent magnet. So right here you would get a DC voltage applied to the coil. And that, of course, is not how a loudspeaker works. We want to drive it over a range of frequencies, so it should be an AC voltage. To make this voltage apply only in the frequency domain perturbation and not in the stationary study step, what we have to do is wrap it in a so-called lin-per operator. Lin-per is short for linear perturbation, and it makes sure that its argument is visible only in the frequency domain perturbation study step. All right? Now this is probably the most complicated step involved in setting up this model. It does get easier from here. So at this point, we should perhaps just take a quick look back at the parameters to check that we have defined everything that I've just applied. And indeed, we have B0, N0, V0, and F0 all defined. Great. The one last thing we need to do in the magnetic fields interface is to apply a velocity to the coil. So after all, the coil is moving up and down. This motion will induce an electric voltage, the so-called back EMF, and that's exactly what this node will do for us. Now this is one place where the power of multiphysics is pretty clear, because what velocity should we enter here? It says 0. We don't really know what the velocity of the coil is, right, before solving the model. So what we do is simply pick the velocity defined and computed by the solid interface, like that. And that's it. All right, over to the next physics, pressure acoustics. This applies to the air domain and the PMLs. So let's remove it everywhere and apply it only to the air domains and the PMLs. We don't want to solve for pressure acoustics inside the solids, of course. There isn't a whole lot of things that we need to set up in the pressure acoustics interface. The motion of the solid will automatically, through the acoustic structure boundary, produce a pressure wave. One thing I would like to do is prepare for a far field calculation, so I will add a far field node to that. This normally would need to go to boundaries that completely surround any sources in the model, but I can use the symmetry in the baffle and select only this one boundary upwards of the entire solid assembly, if you like. The next thing I want to do here is select the type of integral. I'm going to go for a so-called full integral, and this means that you can get your fields anywhere outside the model, not only at an idealized far field distance. So this sort of answers one of the questions I got. Can you get the response at some small distance away? Yes, you can get it at any distance. Over now to solid mechanics. This time we need to model the moving parts. So let's select those. From top to bottom, we have the surround, the cone, we have the former, and the spider, and the coil, and that's it. Those are all the moving parts. Now, we'll assume that all the materials that we have here are linear and elastic, but we're going to use a couple of different damping models. The cone and the former, let's select those first. The cone and the former, those are going to experience an isotropic loss factor, and we're taking that from the material. We have a different damping going on in the spider. It's going to be radial damping with the stiffness damping parameter equal beta underscore SP. That's a parameter again that we defined. And finally, we got damping also in the surround, quite a lot of damping in fact. This again has a parameter beta SU, SU for surround. The very last thing I need to do in solid mechanics is, no, there's one more thing actually. The motion, of course, we're going to have this thing move up and down. It's driven by Lorentz force in the coil. So we'll pick a body load from volume forces, body load, and apply that to the coil. This is the coil domain. And this time we'll select a Lorentz force contribution from the MF or magnetic fields interface. Again, multi-physics. Now finally, what I was going to do is fix some of the boundaries in this model. I'm going to apply a fixed constraint to this exterior boundary of the spider so that it cannot move anywhere, and the same thing to the exterior boundary of the surround. In reality, of course, these boundaries would be fixed or glued perhaps to the frame of the driver, which we're not including here because it has only a marginal influence on the performance. Now that's all of the physics. I'll click on the acoustic structure boundary just briefly to verify that it's applied to the outer surface of the moving parts. And indeed, it looks like it is. This is where the solid meets the pressure acoustics. And the motion of the solid creates a pressure wave, and the pressure in turn acts back as a force on the solid. Now we need to create a mesh before we can solve the model. I could just use the default mesh and be done with it, but let's be a little bit more clever than that. So I'm going to start out with a free triangular mesh, and we'll use that everywhere. So all domains except in the PMLs. And I'm going to make that extra fine. That mesh is going to look like this. Now, if we zoom into the core in particular isn't that fine indeed, and we do need it to be fine there because this is where we'll have eddy currents being formed, and especially at the higher frequencies, those eddy currents will have a very steep gradient. They're going from a very strong eddy current at the surface to a current that's very close to zero, just a small distance into the core. So let's add another size node to our free triangular mesh. We'll apply that one only to the core. I'm going to go for a custom maximum element size of just 1 millimeter. Let's see how that mesh looks. Right, so we now have a much finer mesh in the core, but I'm not done there. I could do even better than that. I'm in fact going to add a so-called boundary layer mesh to the core. This is going to mesh it even finer close to the surface. So I'll do domain and I'll select the core again. For properties, we want to go for all the boundaries. We need, say, 3 layers. Thickness of the first layer should be just 0.2 millimeters. And if you build the mesh again, you can see that you have these sort of rectangular mesh elements close to the boundaries, and they are very, very thin. So that's great. Those are going to be able to resolve our eddy currents. The one thing remaining now is the mesh for the PMLs. PMLs are mathematically a complex valued stretching out of those domains. And if you take a triangular mesh and stretch it out, you would get very sharp angles. That's not good for the numerics. So it's better to go with quad elements. I'll do that by selecting a mapped mesh for what's remaining in the model. Looks like this. Great. We have done our mesh and we want to solve the model. I'll get to questions very, very soon. But let's first create the solver setting. So we have the stationary study here already. We want that to solve only for the magnetic field. So I'm going to remove everything else. Magnetic fields only. After that, we are going to add our frequency domain perturbation study. Frequency domain perturbation. This one asks for a range of frequencies. And of course, we're going to solve for everything with the frequency domain perturbation solver. I'll click this little button to enter a range of frequencies. I'm going to use an exponential range. So we start at 1, that means 10 to the power of 1. That's 10, essentially. Steps of 0.1 and up to 3.5. So 10 to the 3.5, that's a little bit more than 3,000 hertz. I believe that's all we need. I'm going to hit compute and keep my fingers crossed. So the solution is slowly coming along, and meanwhile, let's see if I can answer some more questions. What do we have? Hello, I have a situation that requires a helium atmosphere. How would I implement that instead of air on the front side of the baffle and contain in a tube resonator closed system? Well, you would just select helium instead of air. That's one of the materials that we have prepared for you. That's easy. But then you would also need to make sure to model this tube resonator closed system by effectively just drawing it, I guess. That's the easiest way. You can probably simplify it if it's very complicated, but what you don't want to do is use PMLs like I did, because that would be an open system. Since the working fluid of the thermoacoustic device is a helium medium, this triples the speed of sound, therefore should affect the pressure velocity of the standing wave. Yes, indeed. If you switch to helium, you will get a different speed of sound. That's automatically going to work itself out. Ladies and gentlemen, I believe we have a solution. This solution perhaps doesn't look like much, but it's just one of several plots that we do get. This first plot is of the local magnetic flux density norm, and it's showing that norm for the AC solution at 3,162 hertz. The field, as you can see, is very focused to the coil, perhaps not very interesting to look at. Let's instead look at the stationary flux density by switching to a different data set. And that one looks like this. So the stationary, the permanent magnetic field is strongest in the pole piece, which is to be expected. You can also see that we have a substantial field in the gap around the voice coil. That's also very good. One thing that's interesting to look at here is the local effective relative permeability. What is the effective relative permeability, you might ask? Well, it's simply the ratio between the flux density norm, which we have here already, and mf dot norm h, which is the magnetic field norm multiplied by the permeability of vacuum. As you can see, you can type in basically any expressions you're interested in here. And this effective relative permeability now looks like this. So what kind of conclusions can we draw? Well, where we have high values, over here, for example, where it's red, that means that the core is still operating in its linear regime. We're not really pushing it. We can probably peel off some of the material from this core without affecting the performance. Conversely, we might want to add some material in here in the pole piece because there the local relative permeability is fairly small right now. We have approached or almost reached saturation. That's a very, very relevant and interesting thing to look at. We can also have a look at perhaps the induced current density. You can just search to find it here. Induced. Well, the phi direction is the relevant one. We're going to switch back to the frequency domain solution. If we look at the high frequency, it becomes clear just why we needed to use such a fine mesh close to the surface of the core, right? If we look at a lower frequency, the induced currents will tend to run a lot deeper into the material. Right, that's 300 hertz. We can look at the acoustic pressure in this 3D plot. What you see here is the pressure distribution at zero phase. You can look at other phases if you like. You can also create an animation of how the waves propagate over time. I guess I'll skip that for now because I don't know how well it will transmit over the webcast. We also get a couple of plots of the far field sound pressure level. So this first one shows it for all frequencies and in all directions. I'm going to create just one plot showing the on-axis pressure at a 1 meter distance as a function of the frequency instead. To do that, I'll right-click on results. I'll pick a new 1D plot, and we're going to go for octave band. We will make that a global plot. And in expression here, I'm going to use the so-called p-far operator. And this gives us this computed far field pressure. So we type in p-far with the r and z coordinates for arguments. I want the on-axis pressures. I want r equals 0 and z equals 1. Although this is called the far field pressure, it's not going to be a far field approximation. It's going to be the actual computed field at exactly 1 meter distance. And it looks like this as a function of the frequency in an octave band plot. You can also switch the style if you like to continuous. And with this continuous band plot, it becomes fairly clear that we have a good and relatively stable sound pressure level, approximately from 100 hertz up to 1000 hertz. And that makes this a mid-range speaker. We also have a plot of the stresses and strains in the moving part. They look like this. This is the highest frequency again. The stresses are mainly focused to where the spider attaches to the former. If we look at, for example, say 100 hertz, you will get stresses all over the spider, looking like this. Note also that at zero phase, which is again what we're looking at 100 hertz, the coil goes down at zero phase. But if we look instead at 25 hertz and click plot, in just a second you can see that the coil, and with that, of course, the cone actually goes up. And this coincides with the electric impedance peaking in between those two frequencies. To plot this impedance, we can do a 1D plot again. We can do a global plot of the applied voltage V0 divided by the computed current through the coil, which looks like that. I'll add an absolute value surrounding that to get the absolute impedance as a function of the frequency. I'll hit plot, and we'll also want the x scale to be logarithmic like that. And as you can see now, we do have a peak at approximately 50 Hertz. This plot is a little bit jagged, as you can see, but that's just because I didn't solve for that many frequencies. Now, there are so many other things we could do with this model. We have 10 minutes left. I'm going to try to answer a couple of more questions before going back to the simulation. So one question is, how can I get a sun pressure level from 2 meters away, actually, as this model only has a 1 meter radius space? Well, this model, in fact, only has a 15 centimeters radius space, and I already plotted it at 1 meter. That's the beauty of the far field pressure plot. I could go back to this plot and just set this to 2 instead, and that gives us a plot at a 2 meter distance. Looks kind of similar, not exactly the same, but with lower values. How do you simulate different geometries of coils? For example, a double layer coil in-out or a coil former coil. Well, you typically add one coil domain for each layer of coil that you want to model. You can combine them in a number of fashions. You can model single-turn coils just as well as multi-turn coils. And in 3D, you have even more possibilities, of course, to model coils that are not perfectly round, but perhaps, I don't know, rectangular or have some other exotic shape. Is the spider fixed at the end? Yes, it is. I applied a fixed constraint to fix it over at the end, right there. So what's next? Let's see. Maybe you should mention that the 3D plots are extrapolated 2D data with only radial variation but no circumferential data. That is indeed true. This is an axisymmetric model, and right now the way I've set it up, this is per default, it assumes that everything is invariant with the phi direction, the out of plane direction right here. You can also model in 3D, of course. That takes a longer time to solve, but otherwise the principle is the same. One thing you can actually do in 2D, should you want to, is you go to pressure acoustics and you set a non-zero circumferential wave number. This lets you model phi directional modes with non-zero mode numbers as well. But if you want a true like 3D geometry, you need to model it in 3D. I'll try to answer one more question before going back to the presentation. Oh, there are very, very long questions here. Let's see if I can find a short one. Can you sweep the performance as the coil and magnet heat up? Yes, that's a great question. Indeed. The coil right now, if we can find that over here, has a conductivity, and that conductivity is specified here. It happens to be the conductivity of copper because it's a copper coil, and that goes for most coils, of course. But if you know your metals, you'll know that this is just the conductivity at approximately room temperature. At different temperatures, you will have vastly different conductivities. And indeed, you can model this. You can make it a function of the temperature, if you like, by typing just something in, like plus square root of the temperature, capital T for the temperature, or you could make it an interpolation function like my conductivity of the temperature. You specify your own function, you bring in your data, and you can add parametric solver like this, parametric sweep, in which you sweep the temperature. So indeed, you can definitely measure and calculate how the performance changes with the temperature, and you sweep that temperature across a range of values. Great, let's switch back to the presentation for a couple of more slides before we wrap things up. We had about 30 minutes for this model. There are so many more things you can do, of course. So where do you go from here? I guess one obvious thing here would be to place the driver in an enclosure. You could, of course, just go over to 3D and model the same thing all over again with a cabinet attached. But usually the more clever approach is to use axisymmetric 2D for the electromagnetic model of the driver and extract the relevant properties from there. So typically the BL factor and the blocked voice coil impedance versus the frequency. I did not extract those particular properties from the model that I just showed you, but that is also possible to do and not too difficult. After that, you proceed to 3D for a model of acoustic solid or indeed acoustic shell interaction. As the membrane is very thin, it can actually pay off to treat it as a shell instead of a solid in the 3D model. Now, in any case, this approach of combining the best of two worlds, 2D and 3D, can save a lot of time and effort and still give very accurate results. We have an example model called Loudspeaker Driver and a vented enclosure, which is part of the application library that comes with the software, or you can download it from Comsol.com. Now, let me speak a little slower for a second, actually, because I realize I'm so excited all the time here. It wouldn't surprise me if a few of you felt a little overwhelmed with the example model that I set up. It's basically hard to resist cramming in as much functionality as possible in a demo like this. Now, I certainly appreciate it might be a little hard to follow at times. And probably most of you would be hard-pressed to reproduce everything I did right now. But that's fine. Let me stress that what I modeled was the complete functionality of a driver from applying the signal voltage all the way to producing sound. If you're working with loudspeakers or anything else in electroacoustics for that matter, chances are that you're focusing on some specific part or functionality of your device. And if that's the case, there's likely no need for you to model everything like I just did. I shouldn't say everything. There are, of course, aspects that I left out, but I modeled a whole lot of functionality. You should only model what you need. So, for example, if the driver that you're using is manufactured somewhere else and you're only interested in designing the enclosure, you can choose to represent the entire driver with a circuit model with data from the manufacturer. And that's just one example. If you look at the pictures here, I've done something else, something really simple. I've taken just the surround of my driver. I've fixed it in one end, and I've applied a sinusoidal driving force in the other end. Running this over a range of frequencies, I can then calculate the mechanical impedance of the surround as the applied force divided by the computed velocity. And this will get me a frequency-dependent result, as you can see in this little plot. Now, that model took me literally 2 minutes to set up. It was that simple. So with Comsol Multiphysics, you can model each little part of functionality of your loudspeaker on its own, or you can watch how it all interacts in a beautiful multiphysics model. It's really up to you and your imagination, of course. You just need to know where to stop, and for me, that seems to be very, very soon now. I think we have time for 1 or 2 more questions. Can we eventually evaluate total harmonic distortion of the sound signal due to nonlinear BH curve? Answer is yes. It's a little bit too complicated to explain right now, but yes, you can do that. Can we do time domain simulation? Somebody asks. Yes, indeed, you can do time domain simulation. Can one draw a coil and apply potential to one cross-sectional phase and the ground to the other phase? Yes, if you do it in 3D, that's normally how you do it. Well, it's one way of doing it anyway. Can you investigate what is the root cause for the spike in the frequency response at 700 Hertz? That's very observant of you. I've done that already, actually. What happens is that we get an unwanted Helmholtz resonance right in between the core and the cone of this loudspeaker. And I should stress the loudspeaker, this is actually a model that I set up when I just joined Comsol, like it was more than 10 years ago now. I haven't had the chance to really make it a high-performing great loudspeaker. The design leaves some things to be desired, and this is one of them. We do get this Helmholtz resonance. One thing you could actually do, it turns out that if you were to construct this loudspeaker in reality, this peak would probably be slightly less pronounced than what it was in my curve, and that's because you get some additional damping due to the really, really thin gap that you have between the voice coil and the former. And that damping is something that I'm not modeling in the model right now. I could model it by using thermoviscous acoustics. It's not that hard to do. It's just not included in the model that I set up for you. With that, we have just seconds left of our time. So I would like to thank you all so much for attending this webinar. I hope it was almost as good for you as it was for me. I enjoyed it thoroughly. Now, have a great day today.